Good afternoon, everyone. This is our project on self healing concrete. What is self healing concrete? By definition, a concrete that heals itself, which is pretty much self explanatory. But what does that really mean? Concrete with higher initial cost but is environmentally friendly and will save us money and time down the road. To understand why we need it, first we need to learn the process of infrastructure maintenance. Now, I will be covering three aspects in this presentation: who owns public infrastructures, the types of cracks, and the types of methods of self healing concrete. Who owns the public infrastructure in Canada? Municipal governments own 60% of core public infrastructure. Municipal infrastructure gets people and goods moving, provides safe drinking water, handles our waste, creates spaces for sports and recreation, and helps protect our homes against flooding and other natural disasters. The total value of core municipal infrastructure assets is estimated at $1.1 trillion dollars, or about $80,000 per household. The quality of maintenance. One third of our municipal infrastructure is in fair, poor, or very poor condition. As you can see in this table, bridges are highly maintained with only 1% in very poor condition compared to the other types of infrastructure. Some of the most common crack types: hardened cracks, caused by drying shrinkage, thermal contraction, and structural settlement. This happens due to reduction of concrete volume. Spalling is also another type of crack. Happens when a chunk of concrete falls off due to corrosion of reinforcements as a result of open cracks. However, spalling can't actually be fixed with self-healing methods, although it can be prevented by preventing corrosion to reach the rebars. One of the most common types of cracking is also known as flexural cracking. As you can see from the diagram, this happens due to overloading the structure, and it can happen anywhere on the structure. Now, moving on to a method of self healing concrete. Among the various tests that have been performed, bacteria based self healing concrete has shown to be the most promising. The healing agent is made of bacterial spores and organic compounds and is mixed with fresh mortar. Bacteria based healing. The healing agent is encapsulated so that it is immobilized and protected from crushing during mixing and from the high alkalinity of the cement mix. Moving on to how this method works. Upon crack formation, the weak, lightweight capsules break and healing agent activates and fills the open crack by precipitating calcium carbonate. The bacteria in this case act as a catalyst and transform a precursor compound to suitable filler material. As you can see from the diagram, upon a crack forming, microcapsules are ruptured and the healing agent is released. I will give a few moments so you guys can take a look at this diagram. How it works continued. The bacteria form a thick spherical shell that aid in the survival from chemical and mechanical stresses and have the ability to stay dry for a period of 50 years. Self-healing of the concrete via bacteria occurs through the process of metabolic conversion of calcium lactate to calcium carbonate. Current research being done. In July 2016, researchers in the Netherlands underwent a simulated crack isolation experiment at 8 degrees Celsius. Bead consisting of calcium alginate encapsulated bacterial spores to investigate its ability to form a biocomposite. The bacteria-based beads produced calcite alginate biocomposite after just only 6 days. This was possible because the bacteria-based beads formed calcite crust on the surface. The results of the experiment: after 100 days of this immersion in water, experimental results revealed healing of the concrete up to 0.46 millimeters in bacterial concrete versus up to 0.18 millimeters wide cracks in control specimens. The observed doubling in crack healing was due to the metabolic activity of the bacteria consuming oxygen. In addition to bacterial method, there exist other methods to implement self-healing properties to increase durability of concrete. The most practical methods are chemical encapsulation and LCX. LCX method LCX method is a method where the polymer tendon has a shrinkage process which needs to be triggered by applying heat. In addition to reinforcing steel, as shown in Figure 1, once load is applied to tendon will apply compressive forces to the concrete similar to the case of pre-stress reinforced concrete. The compressive force from the polymer will be applied to crack faces so that the cracks will close. The polymer tendon has a shrinkage process which needs to be triggered by applying heat. The sample was heated to 90 degrees Celsius for 18 hours in order to activate the shrinkage process of the polymer. The results. The results of this experiment tested 12 specimens to compare the behavior of LCX models with reinforced concrete with normal cross section. These models were simulated for 10 years under sustained distributed loads. The results showed a minimum reduction of 10.5% and maximum of 23.5% in crack widths with a mean of 16.3%. Another method called encapsulation of expansive powder minerals. Encapsulation minerals in the concrete are released following crack formation. They will rupture and release expansive powder minerals. Here is a table that displays different testing minerals for the same method. Importance of water in this testing. After the glass capsule is broken in figure, minerals will expand after interacting water and carbon dioxide to form hydrated and carbonated products, which seal the cracks and provide some strength recovery. The healing efficiency of this method was tested under three different conditions: ambient condition, high humidity exposure, and immersed in water. The samples with capsules immersed in water showed the best crack sealing efficiency of 90% in 28 days and 95% in 56 days. This graph shows that regardless of the healing agent used in concrete, water is a very important factor in effectiveness of healing agents. The comparison between healing process of concrete by SHC-D on the far right, which contains the minerals of magnesium oxide and calcium oxide with bentonite in 56 days, with the control group is clearly demonstrated by the digital microscopic cameras. Finally, moving on to the economy aspects of self-healing concrete. Many developed countries, including Germany, South Korea, and the US, are experiencing unprecedented amounts of civil infrastructure deterioration. The annual economic impact associated with maintaining, repairing, or replacing deteriorating structures is estimated at 18 to 21 billion in the US. The American Society of Civil Engineers estimates that $2.2 trillion is needed over the next 5 years for repair and retrofit. Over the last decade, the concept of concrete infrastructure able to repair itself without human intervention has emerged as a possible cure for overcoming civil infrastructure deterioration. Impact on life cycle cost. Benefits of concrete self-healing include the reduction of the rate of deterioration, extension of service life, and the reduction of repair frequency and cost over the life cycle of a concrete infrastructure. As, as seen in the figure, example A and B, the concepted life cycle cost model emphasizing cost increase associated with repair, events for conventional for in, my apologies, events for conventional concrete structure. The dotted lines are for higher performance, higher cost concrete B compared with concrete A. Example C and D. Corresponding life cycle cost and performance when self-healing is included. Well, that includes the end of the presentation. Thank you for joining us.